Another is possible. Here is this color image. These three matrices, the tensor, represent such color image. As many tensor, better resolution.
Professor Predrag, there was some problem in live, so now again you start.
Start. Okay.
From the
No dinner today. Not only no lunch.
It is coming in live.
From now till
Yeah, you start from the beginning. Please.
From beginning. Oh,
yes.
yo. What was beginning? I forgot. First part of today's presentation aimed to one application of generalized inverses and least square solutions in deblurring images. Deblurring images is one part of image restoration problem. Problem is when we make photographing and object is moving, and then picture will not be sharp. And we need mathematical technique, mathematical methods to improve this picture. First was necessary to present picture in form of digits. It is done in form of matrix or in form of tensor. Matrix form is applicable to gray scale images. Each image is divided by rows and columns, and intersection of arbitrary row and column is so-called pixel. And in grayscale image, we will have in each pixel value between 0 and 255. 0 is for black color, biggest value 255 is aimed to white color, and between these extreme values is grayscale scale intensity. Applications in image processing, computer vision, medical imaging, black and white, managing black and white photographs, scan documents, medical images, still actual. Many colors are, many pictures are in color, but still grayscale images exist. Many times our photos in documents are grayscale. In my passport, my photo is grayscale. Probably it requires smaller amount in databases. Then I presented one example which shows equivalence between one grayscale image and matrix representation. Here is one matrix which can be considered as a grayscale image. Here used that 8 is white, Okay, typical in image, how to say, image processing, grayscale image processing. 0 is black, 225 is white. If we want to consider color image, then we must use tensors. Three-dimensional tensors are applicable in processing color images. RGB format is one of possible formats in processing color images. Each pixel includes three values: RGB density, red, green, and blue part. 100 is red color, 001 is blue. Here is a representation of yellow color. Of course, the decimal values here are possible. Here is a color variant of grayscale picture presented left, and there is corresponding tensor for color image presented before. First matrix included in this tensor is matrix corresponding to red part, then second corresponds to green, and then third part corresponding to blue part. We spoke that blurring is phenomenon implied by motion. Motion can be horizontal, vertical, or arbitrary. Can be uniform and can be non-uniform, finally. Here is one example of blurred image, sharp original image, and right is blurred image. But we don't know exact image. We have no exact picture. We have blurred, and mathematical problems which we want to solve is how to obtain original image from blurred one. Here is a grayscale case. Of course, it can be considered in color case. Corresponding mathematical model is given in the form 1.1. What is included in 1.1? Right-hand side is blurred image. From beginning? No? Okay. Right-hand side is blurred image which we have given matrix. X is original matrix, unknown matrix. Original matrix is unknown matrix. We want to find this one. A, C, and AR transpose are matrix which model uniform blur, and multiplication from left corresponds to vertical moving, to disturbing in columns. From right corresponds to horizontal moving. changes rows. Yes, columns, rows. Simplest case is to consider uniform blur, left and right, and then matrices A, C, and AR are represented as toplets or teplets, I don't know how to say, teplets matrix. One kind of structure matrices. Constant. Diagonal matrix, and we have constant diagonal parallels. And so on. Depends on length of moving. So one kind of structured matrices, template matrices, are used to model uniform blur. Left and right. So AC is given if we know in advance that uniform blur implied this blurring. AC, AR are given. B is damage matrix, which we have. X is unknown matrix. How to solve this problem? Mathematically, now it's time for mathematics. Naive approach is to use matrix inverses AC minus 1 and AR minus 1 to solve this problem. Then X naive, it is first approach, inverse of AC, B, inverse of AR. And SVD, singular value decomposition, is used to find inverse of AC and inverse of AR. But there was problem with ill conditioning, and as Professor So told, mainly such problems are ill conditioned, and singular value decompositions, better to say, because we want to find the inverses of two matrices, go to problems. Professor Safik spoke about this. We can speak again with more details or skip only, because A minus 1 or later Murpen-Ross is defined A first. U sigma V. U V unitary matrices, sigma is with singular values on main diagonal. Completely singular values because we want to find inverse of non-singular matrix. N, for example. And A minus 1 is V transpose. V and we know also that sigma 1 to sigma n are ordered in decreasing manner, in this decreasing order. and we have smaller and smaller values of sigma 1 to sigma n, and finally here can be problem with dividing by small singular values, which implies numerical instability, work with big numbers, and the result of such naive image, the blurring was catastrophic. After that, attempt is to use truncated singular value decomposition. Where is use smaller number of singular values, all very small singular values defined as 0, and practically after that we have Moore-Penrose inverse. If we define some singular values as 0, we will have no more usual inverse. One by sigma r and then 0. We use property that 0 dagger is, a dagger is 1 by a if a is different than 0, and 0 if a is equal to 0. A daggers here, we have a daggers. And the result of the blurring was better. I'm trying to find, here is the result of the blurring. Nothing special, not excellent, but much better than previous naive case. What we did, approximated matrix inverse and obtained better results. In one of our papers, we used least square solutions to find, to solve problem of image deblurring. Here is mathematical model of uniform deblurring, Teplitz matrix with main diagonal parallels is included. Why these blocks? Here we have two additional blocks, left and right. Because if we have uniform uniform motion, then object is moving and you will have in photo background. It is background. This background can be defined in many different ways. Some people will say 0, it is black. There are zeros. Another people will use different approximations, something expected behind. Because of that, we must increase matrix from right-hand side by appropriate values, left and right. In block form, it is represented as follows. Gi transpose is one row of matrix G. It is matrix which we want to find. It is given in form H and new matrix F. And practically, we want to solve matrix equation given in form G equals F H transpose. Typically, Moore-Penrose is applied in solving such linear matrix equations. Here we decided to use least square solution. Our explanation was why to use Moore-Penrose solution. Yes, it is best approximate solution of minimum norm. It is least square solution of minimum norm, but for us, minimum norm property is not important. We need smallest least square solutions. And here, if you remember our talk about solving linear matrix equation AXB equals D, you will find here arbitrary matrix which is used to define different least square solutions. Here we decided to use once again previously obtained restoration as arbitrary matrix Y. In this way, we continued restoration. Instead of using only Moore-Penrose part, best approximate solution part, we used least square solution part. There was there we have possibilities to choose Y, matrix Y. Here we analyzed possibilities to use matrix Y, and then after corresponding choice, we performed some numerical experiments. I will show you some of numerical experience. Here is most popular test example. On internet you can find test examples. Most popular is Lena. Lena visited once image restoration conference. And there is a lot, Lena is most popular. And here we presented blurred images. Length of motion in this case is n equals 50. Lena under boundary conditions, under reflective boundary conditions. We spoke about one additional left part and right. Left and right part can be defined in different way. Here is blurring implied by two different boundary conditions. One is periodic, another is reflective. Okay, it requires really a lot of thinking. Here are results of image reconstruction. We used some methods with parameters. Here is with value 55. Here is with much bigger values, and obtain better restoration. As usual, we always is necessary to compare your new method with existing methods. Here is choice 0 for y right. Better choice is to use hard basis with more parameters. So if we choose y equals 0, arbitrary matrix equals to 0, we will obtain Moore-Penrose solution. After that, new problem is noise. We have many different types of noise. You can see here salt and pepper noise, and dots in fog, for example, or wind in desert, and so on. Okay. I wanted to show here application to see that Moore panels can be sometimes applied. Wanted to show influence of ill conditions. It seems that linea is not ill-conditioned case. I don't remember here reducing of singular values. And finally, if we want color image, here will be necessary to apply tensor calculus, which is possible to do later. If we want to solve linear matrix equations, one of applications can be such, the blurring, for example. And now it's time to investigate another kind of neural networks, recurrent neural networks. So far, we investigated only gradient neural networks. It is last time to start with investigation of another kind of neural networks, junct neural networks, ZNN shortly. Is it possible to consider eigenvalues of time-varying problems? Time-varying matrix? No. Think about it, because such neural networks are aimed to solving time-varying problems. Here a typical assumption is that input is given in time-varying form. This type of recurrent neural networks has been proposed in beginning of this century by Yunong Zhang, and it is aimed for solving time-varying problems. Again, we need two global steps to define ZNN dynamical system. Again, first step is construction of appropriate error function, termed as Zhang function, ZF shortly, E of t. You can suppose again 0 of E of t, of error function, is solution of our problem. When we find find solution of equation E of t equals 0, we will solve our problem. Opposite to gradient neural network, where E of t is typically in matrix form, and then we use Frobenius norm of this error function to obtain goal function. Here, E of t is goal function. Error function is immediately goal function. We don't need Frobenius norm of something. And E of t can be not only matrix, E of t can be scalar value, one individual value. E of t can be vector, can be matrix, can be tensor. So flexibility of junction neural network is much bigger than in gradient neural network. Frequently, instead of junction neural network, term is zeroing neural network. Why zeroing? Because we want to find 0 of our error function. In second step, we defined ZNN dynamical system in simple form. Time derivative of error function is equal to, you can recognize our old parameter gamma, gain parameter. Calligraphic F is nonlinear activation, and E of t. Simply, ZNN relates time derivative of E of t with E of t. F is, I will say again, activation function. Gamma is scaling parameter, gain parameter, learning parameter. Also we'll say in machine learning, we say learning parameter. And as usual, gamma should be as large as possible. And then story about nonlinear activation functions is the same. Story about gamma is the same. But a dynamical system considered here is different. If we consider here calligraphic F equals to identity matrix, we will obtain linear ZNN model. And this is, linear ZNN model can be solved analytically. It is not difficult to verify that analytical solution of this system of ordinary differential equation is given in the following form. E of 0, power of E minus gamma t. Again, we can see that initial state is important. All is in hands of initial state. I will put here ZNN dynamical system. It will be necessary constantly. Time derivative of E of t is minus gamma. Scaling parameter F can be used, cannot be used, E of t. Exact solution is if we use limit with t tending to infinity, this term will go to 0, and E of t will go to 0. But we want E of t to force to 0, because we will define E of t such that 0 of E of t is solution of our problem. Because of that, such neural networks are called zeroing neural networks. There is a comment about nonlinear activation. Again, here we have element-wise application of appropriate odd and monotonically increasing function. Again, power sigmoid, smooth power sigmoid. Again, Lie activation function. In this table, we presented here main activation functions which we can expect, which we can expect. Surely you can recognize error function corresponding to matrix inverse. Here is the result. But always here is A of t, and each input in which depends on time. In gradient neural network, we had constant matrices as input. Here we assume that input is in time varying form. It means that this input can be changed during time. Here is state variables matrix. It is an approximation of our solution during time. Again, I will say opposite to gradient neural networks, in which only V of t is depending on time. Here, each input depends on time. And here, we will assume A of t and so on. Only if expression is complicated and we want to simplify writing, we will skip this notation of time. Here is error function which gives solution of which solving a linear system. This one assumes that here is an assumption that A star A is invertible. If A star A is invertible, we will have and what will be solution? V of t will be inverse of A star A times A star, which is Moore-Penrose inverse, but better to say it is left inverse. Such matrix is full column rank. Then dual case. Here, what is here with lambda? Tikhonov regularization. This method is applicable in computing Moore-Penrose inverse of arbitrary rank diffusion matrix. Lambda is chosen with smaller values. Solving nonlinear equation. Square root. And finally, it is square root of number. And here, during our lectures, we will consider scalar values, we will consider vectors, and we will consider matrices. It is a short comparison between GNN and ZNN. We can split recurrent neural network, continuous time recurrent neural networks in GNN class, gradient neural networks, and ZNN class, junct neural networks or zeroing neural networks. Gradient neural networks are aimed to constant case, time invariant case or constant case, we will say, time independent. Opposite to this, ZNN is aimed to solving time varying systems. Time varying systems are systems which exhibit dynamic behavior which is subject to changes in time. Many systems are time varying systems in biology, during evolution. Time varying, my colleague from Greece investigated time varying case. Much better is to investigate problems in economy as time varying than static. Okay. Here is our start in defining ZNN models. In a material which you have, there is one working version of book, and this book includes scalar valued input, vector valued, and matrix valued. Here, during our lecturing, we will present scalar valued and matrix valued. I think after that, in middle, vector valued input will be clear. We want to solve, we want to find the inverse of time varying scalar value. E of t is TV, time varying scalar. For example, E of t can be sine of 3x plus 2, 3t, sorry, 3t, we consider here dependence on time, so on. How to define ZNN model? First, we need to define error function. Error function can be defined in different ways. A natural way how to define E of t is given in 3. Ax minus I. Where is case xa minus 1? Here we assume commutativity. If we solve ax and xa, so only one such case. It is natural and simplest way how to define error function, but theoretically we can define error function until 1 p.m. What do you think? slightly longer until 1 we will work. Here is another way to define error function. It is really artificial way to define error function to find matrix to find scalar inverse, but theoretically possible, and we will consider here. Another one is dual case. Third one is also possible. Then, according to error function, we will define ZNN models. Here are presented ZNN models and corresponding Simulink implementations, better to say. My idea was to analyze at least 3 cases. After all, questionable is we will analyze first one, of course. First one is most simple, natural way how to find inverse of scalar value. But theoretically, we can use error function 4 and so on to 5, 6 to define ZNN model. Now you are experienced in defining ZNN models, and someone of you using this error function can define ZNN model. We have E of t equals A of t, x of t minus 1. Not identity matrix, 1, scalar value we consider. It is priority of ZNN. We can consider also scalars, vectors, tensors. And we have model dot of t equals minus gamma E of t. A linear model we will consider. Of course, always we can put nonlinear activation. And who is willing to make okay, now we will define expanded form E dot. We need E dot of this. Find time derivative of this. Nothing simpler. E dot. Dot. Can they see this dot? No, of course, dot. X dot. Invertible mass matrix is assumed. E dot left. It is E dot, of course. A dot x plus A x dot, nothing. Derivative of product. It is derivative of product. Well known from high school. I think in high school we learned this.
E dot t is equals to minus gamma E of t. Output. I combine.
Okay. You made this model is applied. Dots are not visible. Even we was confused. Are not visible. E dot of t is equal to minus gamma E of t minus 1. It is not minus 1. But it is implicit form of ordinary differential equation. Here we have only one equation. It is not system. Because how to solve this problem if system is in implicit form? Aha. Okay, yes.
So we have to, so we can solve it by linear solve or either.
Better is to transform this in explicit form. Add left and right in both sides x dot. Yes, it's time to start with jungle neural networks. We are in second half of our course. Gamma, better gamma. It looks as V, for example. Okay, yes.
So this will be 1 plus A of t, so we take inverse.
Then we will move this to right hand side and obtain x dot equals of t equals.
This will take
Here we will have 1. Are you sure? Plus will be plus.
We keep this side and we move this everything
inside. You want to move in this way.
So this will be these two things will be getting.
Okay, we move from. I had idea to move this right. Looks simpler, but we can move from another side. No problem. We can see what is here. Better is to move from left. This from left to right. Then we will have analogy. Okay, x dot stays. Dot. Here will be minus. This term will go to another side in minus. X dot. Then
Remaining as it is.
another one. It is our first ZNN model aimed to find inverse of time varying scalar value. It is as in 7, you can see. Now we will analyze ZNN model and later we will see practical work in this Simulink. Can you recognize where is our beginning? Where is beginning of this juggle called Simulink model? E of t. We used interpreted matrix function. Double click on this A of t will open definition. Finally, we can put here only A of t and use our command line to define A of t. I think our first example will have definition A of t equals sine of 3t plus 1. We can use A of t equal and then we will have problem in which point we will have problem, in which time instant. T equal 0 point. Thank you. We will have problem. but it is possible that moving during time will skip 0.1. 0.1. If not, there will be problem. It is beginning A of t. We need 1 minus A of t. 1. Here is constant 1. Block with constant value. We need block with constant value. 1 minus A of t product with x dot. We must use s dot before integrator. It is slightly, yes. Because x dot is defined by x dot, 1 minus A of t. After that, we need x dot. X dot is here before integrator. And it is with plus. Then we have two another terms with minus. Plus minus block. We need minus for A dot x. We need A dot. Here is block for derivative. Then we need product, multiply A dot with x. X is after integrator. Here is integrator. Or just before integrator we have x dot. After integrator we have x. And we need third term. Third term is minus gamma, error, minus gamma, error function. It is ax minus 1. We need ax first. A is input. Then x is after integrator. And then we need to multiply ax minus 1 by gamma and put output signal from gain parameter to minus here in plus minus. And all right hand side term is x prime. After integration, it will be transformed in x. And again, the same story. We can go back to another time instant if to another time instant in case if time interval is not finished. When time interval is finished, we can put current value of x of t in to workspace, or can make plots of x of t. Can use norm. Can use error function. Error function is ax minus 1. Present error function. Plot graph of error function. It is our first model. I think we will have time for one more model. Model 4. Who is willing to develop ZNN model for 2? Elementary calculus, really. Do you want? Are you not ready? Do you want? No? Colleague? You want surely? Please. Nothing easier. What? I will help, of course. Of course. Why not? Oh, I will clean the table. Here is ZNN design. E dot equals to minus gamma E of t. Okay, here is of t. E of t is defined as x. Can we skip of t? 1 by a. Okay, then E dot left, more left. E dot is equal to. Of course. X dot. Then composite function. Chain rule. What was the name? No, of course, will be. It will be. It's true, will be. But we first need to compute E dot. It is X dot. Then we need plus. Continue, please. Composite function. Plus 1a square and then a dot. Composite function. Very simple. Simpler than GNN, but typically right-hand side is in one.
A of t with respect to time. A of t.
One.
One by S.
Okay.
Okay. Okay. Minus 1 by S.
Because of that, here we have plus. And it is equal to minus gamma. We can continue. Here is, yes, we are here. Then we will multiply both left and right hand side by a square. Typically multiply by a square, left and right hand side. And we will obtain a square. This we will multiply now, but also right hand side. Design Simulink, I hope, requires some time. If you have MATLAB, you can try. Have you installed MATLABs in your computers? Have? Okay. What happened?
T is equal to?
Sorry. Equals minus gamma x minus
1 by A.
1 by a, yes. Multiply by a square. we will obtain a square x dot plus
1 by A dot
now then minus gamma a,
X.
a square or x a square the same a square minus a no minus a minus a now we will add here is it the same? Yes, left x dot and right and obtain x dot equals
minus A square.
we 1 minus a square here is minus a dot should be it is here it is our ZNN model. Simple way looks only complicated than GNN because of plus, plus, minus, because of derivatives of product and corresponding ZNN model. Okay, thank you, thank you. It's time for lunch, I think. I promised we will have no lunch, but we will have. If you have some questions.
Thank you very much, Professor Predrag, for your wonderful lecture. Audience, if you have any questions, please, you can continue.
So for a particular problem, we can define the error function as we want in multiple ways.
As we want.
But the choice of error function affects on the convergence, or it does not affect on the convergence.
This zeroing neural network, design of zeroing neural network, force E of t to 0. Because we wrote here analytical solution. Analytical solution is E of t equals 0, initial state, times exponential term. E power minus gamma t. Here is all visible. Exponential convergence is visible, and visible that bigger gamma will force faster E of t to 0. This exponential term goes to 0. Even better visible than in GNN.
But still, some of the error functions will give higher numerical oscillations and some will give less. So how will we choose
Possible. Finally, we presented here one possibility of division by 0. And sometimes we can. What will be with ill conditions in this case? Division by 0 is difficult problem here. We used in one paper to add one small parameter, 10 minus 16, I think, available in MATLAB, but only slightly skip this division by 0. In ill conditions can obtain finally because we go from one time instance to another time instance. And in each time instant we have one constant problem. but use classical numerical methods from initial state, solve problem. Then use classical numerical method in another time instance. And another time instance is very complicated. Because of that, Jung neural network is more efficient. Zeroing or Jung is the same. It is. Jung was originally last year's zeroing. Probably Jung don't want to call this neural network. Even in China, they told me zeroing is more frequent.
Okay, is there any other question?
If no question, give big thanks to.
Thank you. Only one question. Okay.
So now we have bracket.
Lunch. Solution. In mathematics and computer science, computer algebra is one very popular topic. Also, another name for computer algebra can be symbolic computation or algebraic computation. It is a scientific field that refers to study and development of algorithms and software for manipulating mathematical expression and other mathematical objects. So object of manipulation in symbolic computation are not only numbers. Object of manipulation can be symbol, which means symbol as one unevaluated object, can be formula. Object of manipulation can be function, and we will be able to apply another function to our previously defined function. In this table, I presented shortly difference between numerical and symbolic computation. Left column includes examples about numerical calculations. Right column, here are examples. 2 by 6 is approximately in numerical calculation 0.333 and so on. And we lose immediately after, in first step, we made approximation. What can we expect in later calculations? Symbolic calculation will only simplify 2 by 6 in 1 by 3. Numeric computation can calculate x plus 2x equals 3x. What does it mean? Symbolic computation is able to manipulate with unevaluated symbol x. Another example, cosine of. Also, symbolic computation is able to make some simplifications. Example with trigonometric expression, example with differentiation, with integration. Here is numerical integration. In right column is symbolic integration. One formula for simplification is presented right. Numerical calculation performs evaluation. Symbolic computation performs simplification. Here are several another differences between numerical and symbolic calculation. Here is sum of two integers. Result is integer. But here is sum of two expressions. In both expressions, one unevaluated symbol x is included. Result is given in terms of these unevaluated expressions. Numerical calculation will give such power as numerical value, not able to give exact result as it is case in symbolic calculation. And so on, we can make many such examples. Numerical calculation, difference between two numbers. Symbolic calculations, difference, addition with two expressions. Most difficult problem in symbolic such kind of simplification is desirable in symbolic computation. If we have no such simplifications, then obtained results will grow rapidly, exponentially. What can we expect of symbolic computation? First, we can expect computation with arbitrary precision numbers, with no rounding, and with no problems about ill conditioning. Computation with symbols and variables. Computations with functions. Standard functions, there is a number of standard functions, and also computation with user-defined functions, manipulations of formulas, symbolic differentiation, integration, factorization, and so on. Simplification is most important tool. Also, computer algebra system is one complicated software program which includes user-friendly interface. It means that interface enabled in such software program must be appropriate for easier programming. Computer algebra system can prevent difficult algebraic manipulation tasks. For example, if we want to compute such expression by hand, it will take days and night, and finally you will make one mistake. In Mathematica, it is simple job. X minus 1000 can be bigger, can be power x minus 100 power 1000. Where is Mathematica? Shift enter will give evaluation. Shift and then enter. Okay. don't want to work. It is strategy of Mathematica. Okay, I want to save x minus 100 to 1000 for future using. Probably it will be possible to simplify and so on. But I will say evaluate, please, expand. Percent is last exit. I can use copy paste and not append, expand. Of course. Looks fantastic. Be a researcher in mathematics, in linear algebra, and don't use Mathematica is really difficult to understand. Don't use such tool which can help you. Arbitrary precision, big, extremely big coefficients. I cannot scroll because of one part for sharing. Simply I will delete this output. One simple 2x plus 3x 5x. It is interface of Mathematica. Behind Mathematica is Mathematica programming language, Wolfram programming language, kernel of Mathematica. We can see that here we have inputs and corresponding outputs. Inputs are denoted as in of 1, 2, 3, and so on, corresponding outputs out 1, 2, 3, and so on. We can return back to expressions. And then here will be in in of 4 and so on. It is as our notebook. We can go back to make corrections and trace behavior. This language based on programming language based on questions and answers is called interpreter-based programming language. Opposite type of programming languages are compilers, such as C++, C#. We evaluate, obtain executable version, and then we can work with this executable version. Here is not executable version. NB extension is obtained in Mathematica. User interface is desirable. Here is user interface of Mathematica. We can save this, of course, file save as NB extension notebook. It means notebook is extension here. Programming language. Of course, Mathematica is not only type one expression and obtain result. behind Mathematica is a programming language, Wolfram language, and we will be able to to make programs to define our functions. Simplifier is desirable. Memory manager, garbage collector. Arbitrary precision arithmetics. For example, 1000 factorial. It is one number. 10,000 factorial. Here is list of most popular symbolic computation tools or computer algebra systems. Maple and Mathematica are dominant. Maple is developed in University of Waterloo. Mathematica is universal computer algebra system developed by Wolfram Research Group. Here is list of symbolic computations tools such as substitution, partial derivatives, solving linear systems, matrix equations, compute limits, symbolic integration, and so on. 1 hour is a really small time to say something more. Statistical computation is also there. Theorem proving. Finally, symbolic computation is able to confirm or to your hypothesis or cancel your hypothesis. History of symbolic computation started in 1960. First symbolic computations tools was list processing with strong computation inside brackets. MATLAB has possibility to work symbolically. Here is list of computer algebra systems. Of course, it is only to see evolution of computer algebra systems. Now we will see more details about package Mathematica. Short, I will use short version. We spoke that Mathematica is interpreter-oriented programming language, and we have number of inputs and corresponding outputs. Inputs are denoted as IN of number n, which changes outputs as out of n. Here is possibility to ask questions about Mathematica. I will ask some questions if you have doubts. For example, I can ask about function log. Capital L. All standard functions in Mathematica start with capital letter. Here is answer. Log of z gives natural logarithm. It is logarithm of base e. If we want another base, we will use syntax with another parameter. If we want more detailed information about function log, we will put two question tags, shift enter after that. We obtain more informations, which three future properties, listable, which means log is applicable to lists. Log, list, for example, 1, A3, we obtained three successive values, log of 0, a log of 1, 0, log of A, unevaluated, weights, Mathematica weights. I don't know what is A, blue, A, not defined, and then Mathematica will weight. If I define A, then log of A will be computed. Log of 3, weights, log of 3. I can ask Mathematica to give me value of log of 3. Give me numerical value of log of 3. And 2/ means numeric how to say, application of function after expression. Postfix. Application give me log of 3 with 1,000 decimal digits. Give me value of p in 1,000 digits. TP, 1,000 really powerful tool, very useful for mathematicians. I will delete this exit to save space, or otherwise I will have a heavy job to scroll during this notebook. Then numeric function, if we apply to numerical value, we will obtain the same, we will obtain numerical value. Protected means we cannot use log function, for example, in assignments. Log symbol is protected. It is okay. Imagine that user is able to change log and make mess in Mathematica. Which data types are available in Mathematica? First, we can speak about constants. we already used pi, how to say pi. Then exponent function, degree, complex unit, capital I, infinity. Where is Mathematica? Here is 1 plus infinity. Of course, infinity. Infinity plus infinity. Infinity again. We can use palette and then different assistants in typing. Basic math assistant. And here we have possibility to type mathematical expressions as in Word. It is the same as you type formula in Word. But after Shift Enter, we will be able to evaluate this formula. Here is pi. If I press Shift Enter, what will I obtain? We had such situation. What was log of 2? Log of 2. But when we force Mathematica to evaluate it, will be, I think, the same pi. Of course, I know it is pi, and we will see later. And if we say evaluate, please, with wanted number of decimal digits, Mathematica will evaluate. Different types of numbers, integers, rational numbers, real numbers, complex numbers. Complex numbers are in the form real part plus imaginary part times complex unit. Here is possibility to use plus plus minus minus in front or after, as it was in C++. Plus equal, I think all familiar with programming. C++ programming can recognize. Then several examples which I had for my students, 3 plus, I plus plus, or 3 plus I. Typical questions. Can works with strings. String is arbitrary sequence of characters between quotations. Real rational numbers, complex numbers, lists. List is ordered set of objects. Elements of list can be of arbitrary type. In one list, we can include elements of arbitrary type. Test functions. This table contains list of test functions. How can we recognize test function? Q in the end of name. Q in the end of name means it is predicate function. Output is true or false. We can ask a question if input is integer. Even integer, odd integer, prime, is it prime number? Is it number? Is it numerical value, polynomial, vector, matrix? Is it matrix? For example, we can ask question, is 13 prime number? Answer is true. Is this number 10 power 100 plus 1 prime? Not. We can convert rational numbers to real numbers with arbitrary precision. Here is number of decimal digits in transformed real number. Of course, rational number is exact, and in this transformation we can choose arbitrary precision. Round, floor, sailing, standard functions for integers, sign, absolute value. Integer digits. Integer digits of n will give you digits in decimal. I will put this Mathematica. I didn't use copy. Control C, Mathematica, Control V. If we use only integer digits and then one argument, Mathematica will give list of integer digits. In C++, we will need one while cycle with div and mod included. If we put comma 2, we will require digits in number system 2. It will be a transformation from decimal number to number system, to binary number system. Number system with base 16. Of course, then 11 is legal digit in number system 16, 11. It is C. There is list of numerical calculations, possibility to simplify rational expressions, several basic functions for complex numbers. Complex number with real part x and imaginary y. I is complex unit, real part, imaginary part, absolute value of complex number, conjugate argument. Random number generator, random with classical syntax, random, and then we can choose which kind of numbers will be generated. We can decide about precision. We can give beginning and end of generated numbers interval in which such numbers will be generated. Mod div minimum, greater common divisor, least common denominator, prime p gives the number of primes less than or equal to x. Pi is notation of this function. We can try. I started to type inside result. How many prime numbers we have from 1 to 1000? 168. Answer. Much bigger number can be here. 2,078,000 and so on. Quickly. 10,000 factorial. Transcendental functions. Lists, one-dimensional list includes arbitrary sequence of values between brackets. Use PDF and then copy-paste in Mathematica. Here is one list. First, enter. If we have function, we can press enter. We can give name of this function, of this list, L, first of L. L of 2. L of 1. L of 3. What is value of A? A. Undefined so far. Then we can define matrix. M matrix is equal to two-dimensional list. Elements. Result is two-dimensional list. We can ask matrix form. Of M, and it is much better visible for us. Inverse of this matrix. Will we have problems? will. Matrix M is not square, no inverse. But there is our frequent topic here, pseudo-inverse. Pseudo-inverse Mathematica uses long names, very, very long names, never shortened, always long names, initial capitals, and are always rule of M. It can be simpler. It can be simpler. Mathematica is not sure if A, B, and C are complex or real. If we say that A, B, and C are real, result will be simpler. In this case, Mathematica wants to work with complex A, B, and C. What can we do with polynomials? We can define polynomial in arbitrary number of variables. Here is polynomial of one variable. What Mathematica did only organize the factors in different way. We must ask Mathematica to expand. We must ask Mathematica to do opposite. Factorize of t. Here we obtained even better than in original S. Factor 2 in front, because from this second expression we can use factor 2. Collect, expand with respect to different variables. First x and then y. Factor such expression x power 10 minus 1. If we divide factor x power 10 minus 1 with x minus 1, we should obtain simplified version. Yes, there is not factor x minus 1. Expand percent is last expression. not expand, expand. But now percent is different. I cannot not use more percent. Now I must use copy, paste. Because percent is this incorrect mathematical expression. Coefficients, we can find coefficients in polynomial with respect to selected variable. Coefficients of t x, 3 coefficient in front of x power 3. And many other functions for transformation of polynomials. Cancel polynomial in numerator and denominator. Expand polynomial factors. We can divide polynomials and ask remainder, ask quotient of two polynomials. Polynomials can be of one variable and can be of more variables. Then we can ask a remainder or quotient with respect to wanted variable. Here we have polynomials of two variables and we ask a remainder with respect to variable x. Simplify function for simplification. Most powerful if we ask value of sine square plus cosine square, I expect, no, from PDF to sine square of x, x is unevaluated, plus cosine x square the same, but what is simplify of this expression? One simplify function is most power and most important function here. simplify if I use here. We can solve equations. Space. If we don't put space, it will be one variable AX space plus BX plus C equal 0. 2 times equal here. Equal. If we put equal only once, it will be assignment. Yes. Simplified C, evaluated C with respect to another part. In this case, all 3 variables, all 4 variables A, B, C, and X are unknown. We can specify variable with respect we want this equation to be solved with respect to X. And here is our well-known solution from 2nd class of high school, quadratic equation, and here are 2 possible solutions. Solve this equation of order 6 with respect to X. Of course, we must obtain 6 solutions. Some of solutions are real, and other solutions are complex. We can ask a numerical value of this. Give me numerical value. We will see that that 4 solutions are complex numbers. Here is a complex unit in case when Mathematica gives this as output. There is n solve, which will give us a numerical solution. We can try first with solve. What will solve say? Try with solve first. Solve will give exact solutions. And solve will give numerical solution. We can ask solutions in real domain, solve this matrix equation in real domain. Then we obtain two solutions. Of course, since this equation is of order 4, we have 4 solutions, and 2 of them are complex numbers. Then we can solve systems of linear equations, systems of nonlinear equations. System is presented in brackets. First equation, x plus, ax plus by equals 2 times equal, don't forget, otherwise we will not give solution. X minus y equals 2, comma, and then you can specify with respect to which variables you want solution. With respect to which variables, x and y. Finish with the function, shift enter. In this way we can solve arbitrary system of linear equations. Nonlinear equations can be solved. Minus 1 with respect to x. Reals means of course, equals 0. We must have equation to solve, or system of equations. Arbitrary x, then we will obtain 4 complex solutions. Reduce is able to solve system of inequalities. We will try with one system of inequalities. There is function find instance applicable to system of equations and system of inequations. In this way, we can use find instance to find solution of constrained system of linear equations. Or we can use find instance to find solution of equation in case when it is not easy to obtain solution. Then we want one particular solution. Find instance will ask particular solution, obtain something as solution. Differentiation, derivative of x power n with respect to x, n times x power n minus 1. Derivative of x 1 by A, our problem from morning, by A. Derivative of sinus of 3x minus 2 with respect to x derivative of arcus tangens. Second order derivatives are available, arbitrary order derivatives. Can use Mathematica to solve differential equations, solve system of differential equations. Solve. With respect to t. The solve says solve here is not appropriate. Better is to use this solve. E of t, comma t Capital E is standard for value 2.71. I wanted to use from ZNN, from our ZNN model. I must use here something different, F, for example, or A1. Here is solution of our general ZNN model. It is our general ZNN model. I asked Mathematica to find exact solution. Minus gamma initial state times E minus gamma t. We spoke, Mathematica gave solution. Limit. Can we ask limit? Limit of this tends to infinity. Limit is I will ask help, Wolfram documentation, help me about limit. Limit of function when of function with respect to x when x tends to particular value. Okay, I will use this solution. And ask limit when t tends to infinity, 0, as we expected, because ZNN is aimed to find zero of error function. Finally, this term e power minus 1000 t force f of t to 0. Then we can define inverse of invertible matrix. It will not work. Random, real random integer. Better visible. Link. Minus 1, I from 1 to 3, j from 1 to 3. Hilbert matrix, 3 times 3. Rank, what is rank? Matrix, rank of who I didn't assign. H equals matrix rank of H 3, inverse of H. Inverse of H. Determinant of H. Eigenvalues of H. Some equations which should be solved. possible. Can we ask numerical value of this? Aha, it is. We obtain numerical value of this. Okay, and so on, so on. They told me 1 hour. Aha. Okay. If you have questions, okay, you can ask. Finally, I have sense that you are tired. You require rest, I think.
Here we find the determinant of, derivative of sine 2x minus 3.
What? Did,
Here,
which slide? Determinant of?
not determinant, derivative.
Derivative of sin x.
Of?
Derivative of sine x.
Yes.
That is derivative of sine 3x minus 2 gives 3 times cos of 3x minus 2. But here 2 minus 3x.
Two minus 3x. 3x.
Here use cos of minus x is cos x. It's same.
I don't know what to say. Help for D.
Here cos of minus x is x on positive function.
dfx gives partial derivative with respect to x. D of sinus of x with respect to x. D of 3x minus 2 with respect to x. All correct except
Sir, it is also true. They have taken the common minus sign common. Cos of minus x is cos x. So it is true.
derivative of sinus is cosine. Sine, cosine. Cosine of 3x minus 2 times derivative of 3x minus 2. It is true. Minus here. Correct. It is correct. But what is with derivative of Derivative of?
X to the power n.
Can you type here? Derivative of?
X to the power n.
Can you?
X to the power n.
X to the power n with respect to x.
Yes.
Fine.
It's 1 minus n or n minus 1?
No, plus. Here is visible as minus. Plus.
It is
Plus. It is plus. Here is plus. Believe me. Believe me.
Yeah, it
Plus.
is looking both are minus.
Who don't believe can go here in this. Plus. Visible is minus. Otherwise, it's plus. Okay, more questions. Thank you. Okay.